Okay, so our next speaker is Stefanella Boatto, who is a local from Federal University of Rio de Janeiro, who will speak on vortex dynamics on surfaces of revolution.
Thank you, Walter. Thank you, the organizer. So I have to warn you that this morning my computer crashed. So the presentation that was supposed to be shown is not there. But I think also the computer made a choice that was not a good presentation. So I have to. So, okay. So there will be a little bit more of the slides than I wanted to. Anyway, so working on vortex dynamics in general and on manifold in general, I learned a lot working with people in celestial mechanics and in fluids. It's a great playground for this kind of interaction, and this has to be here or there. I think it's how it works. It's not. No? Okay. So first of all, I want to say that 2 years ago, in fact, we organized another similar event, and this was in honor of Asana Recht, that for sure was one of the mentors in this area, that really collaborating, putting a lot of dynamics in crossing different kind of areas. And in fact, I have to say that there is a lot to learn even, in this interaction of the n-vortex problem and the n-body problem. And they have so much more in common that we might think in the first, at the first look. So, since my computer crashed, I decided that it's better to start from conclusions. So at least I give you 3 punchlines, and if you fall asleep in the rest of the talk, then you can fall asleep, okay? So what is the first punchline? So to do 2D vortex dynamics, and this is a punchline that I have to credit to Kimura as a beautiful paper in the Royal Society of '99. If we have a manifold with a metric G, we need the remaining metrics also to compute the fundamental equation. That is our Poisson equation, which solution, given a vorticity field distribution, the solution is the streamline. Streamline will play the role of the Hamiltonian for a point particle. Then this streamline enters in this Hamiltonian formalism, then underline has a symplectic form. So we have a manifold where actually we need 2 structures. We need a remaining matrix and a symplectic form that is nothing else than an area form, an appropriated area form. So it's in geometric language, these 2 objects have to be compatible to go together, and we will use a lot of this correlation. Given a matrix, deduce what is the corresponding area form to deduce the appropriate coordinate. Okay, the second punchline is that we have to be careful if we deal with surfaces that have constant curvature, constant Gaussian curvature, and no boundary, like, for example, the sphere. We put a vortex, nothing happens, you just stay in peace. But then what happens if I deform that sphere? If I deform a sphere, for example, in an ellipsoid, and here, for example, even an ellipsoid of revolution, by magic, our vortex start moving. And we'll see that, in fact, this is a sort of the classical equivalent of the equivalence principle of general relativity. In general relativity, we have the variation of the space-time are equivalent to a force field. Here we have the variation of Gaussian curvature of our manifold, 2D manifold, are equivalent to a vorticity distribution. And then, well, there was another thing that is kept. Okay. Anyway, so what we have here, we have that is divided into parts. First of all, I will just briefly go over the dynamics on the plane to see how to construct the vortex dynamics from the particle dynamics, and then we go to manifold. So, what is the vorticity field? Well, I believe the audience knows, but just for sake of it. And what is the point vortex? Point vortex is roughly a singularity of the vorticity field. And we will consider always incompressible flow. So we have, if R is the position of a particle and U is the corresponding velocity field, we introduce the vorticity field being the curl of the velocity field. Now, in 2D, if we see 2D as embedded in R3, we can set in each point a set of coordinates where, we have that E1, E2 are tangent to the plane, and E3 is the perpendicular direction. And then we have that in these local coordinates, the coordinates of the particle is just two coordinates, and the vorticity is just pointing in a perpendicular direction. Now, some example of vorticity fields of interest. I'll talk about point vortices, meaning delta distributed vorticity field. David Risher will talk about vortex patches later on this afternoon, I think 2 o'clock. And so what about point vortices? Point vortices are characterized, each point vortex is characterized by the position of the vortex, R0, and its strength, vorticity strength. So this strength one can understand using the circulation. If I take a curve around this point vortex, by using just the circulation and Stokes' theorem, we see that this is really the circulation of around the point. And so if we have our point vortex and we have a particle, a test particle, this will go just into circular motion. And of course, the point vortex can make particle rotate clockwise or counterclockwise, and we assume that it's positive vorticity for gamma counterclockwise, and clockwise is negative. Okay, so example of vortices into nature, we have cyclone in our atmosphere and the atmosphere of planets. Of course, this is a three-dimensional structure, but we can see this as tracer spiral around our vortices. Now, this is the motion of a particle in the field of vortex will undergo to the circular motion. Now, what about the point vortex himself? What about the dynamics of the point vortices? Underlying this, of course, we can deduce this directly from Euler equation, and there are beautiful work by many people, and the one that's dear to me is the work by Marchiori Purvirenti in the 90s, but one can also make an answer. One can just say, okay, and this is the answer that basically is underlying many fluid dynamics papers. Let's consider as each vortex behaves a particle in the field of the other vortices. Now, just by these answers, what will be the dynamics of two identical vortices? So now I consider the vortex 1 is the particle in the field of vortex 2, so this will make this turning around. And at the same time, vortex 2 is a particle in the field of vortex 1. This makes going around. The combination is just a rotation. And now, a little bit of history. This idea of particle going into circles was already present, I always say, in the Occidental culture, because I don't know about the Chinese or Indians. We have a representative here. What is the tradition there? So I have to apologize. So Descartes has, in the 17th century, was talking about vortices motion even as a periodic orbit, but even later on as a theory for kind of explaining the solar system dynamic. And in fact, for him, the sun was like a big vortex, and these planets were going around. Of course, this was not was not a kind of idea that would give rise to stable motion. And in fact, Newton, 40 years later, came out, we know the theory of gravitation with a different kind of story. Now, much later, the vortex theory comes at the very tiny scale, at the atomic scale, because at the time we didn't know even about the structure of the atom. So again, William Thomson, that is known as Lord Kelvin, came out with this model of a vortex atom. Now, do not ask me why the vortex atom has to be dimensional. I don't have a clue. But the idea was roughly that the atom was like a positively charged in this outer layer, and the electrons were sort of vortices. And to balance the repulsion and attraction, they were arranged themselves into regular polygons. So the question was, what's the maximum number of vortices or electrons that I can put before this structure breaks down? And there is, I didn't find the 83 paper, but I found the 1904 book about electricity and matter. And it's beautiful because, okay. Here you see they were talking about this triangular, and then they were talking, as I said, many kind of concentric polygonal figures. And they were doing experiment in Cambridge on the River Cam. They were doing experiment with magnets, and they were floating magnets on the River Cam about this. So then other example of this kind of polygonal structure we've seen in superfluid helium. It's too bad John is not here, but this here would be the magnetic field line coming out of the plane, and this will be just an horizontal cross-section. And you see that they do arrange themselves as regular polygon, a square, a pentagon with a center vortex, and here we even have a triangle with, I don't know, many vortices, 8 or 7. So this is why, we got interest in studying relative equilibrium, and we were not the only one. As I say, Thomson studying the linear stability starting in the 19th century, and eventually the study of Thomson's was actually about linear stability was completed by David in his, I think it's PhD thesis now. But actually, David was very close to nonlinear stability as well, because in this business, to do linear and nonlinear stability is basically the same thing. Because what you have to do in both cases is just to compute the eigenvalues of the Hessian of the Hamiltonian evaluated at the equilibrium. Once you have these eigenvalues and you identify the zero eigenvalues due to symmetries, you have both linear and nonlinear stability at once. So this was somehow did Cabral and Schmidt in a later paper. These are analytical estimates that they did in the planar case. Has the sphere concern, we have, again, several people work on that. We have Marsden that did the case of 3 vortices, even of different strengths on the sphere. Then we did the case of the ring with and without polar vortex, or a ring with 2 polar vortex. And there are beautiful papers even about the existence of several rings on the sphere. And I have to say that all these things, all this ring structure, you see even for the n-body problem and for the n-charge problem. Because as I say, this is, they're strongly connected. And the physicists already saw this in the 90s, but by a slightly different procedure. But they got to the same conclusion. And but going back to our business, how to derive the equation of motion. And so the first step is to derive the dynamic of the particle. because once we have dynamic of the particle in a given vorticity field, so we have our vortices moving around, and we say my particle is there, how the particle dynamics is affected by the vortices. Then in the second step, I can derive the vortex dynamics with our answers, that each vortex behaves a particle. So let's start with the example of R2 on the plane. As I said, we have our particle with two coordinates, x and y. We have the velocity field, and we have the vorticity field, and we introduce this incompressibility condition. Now, incompressibility condition was already from the 19th century. Kirchhoff realized that the incompressibility condition allowed us to introduce an unknown function, the stream function, that allows us to rewrite the velocity component into this Hamiltonian form. Because, in fact, if we use this and we plug in here, this is automatically verified. Now, in this formalism, psi plays the role of the particle Hamiltonian. And notice that x and y are a pair of conjugate variables. So our configuration space is also a phase space. That this is very strange for example, celestial mechanics, because this is very strange for them. So this is why we look at our plane not like a generic, as I said, Riemannian manifold, but as a symplectic manifold. So here we have our equation, but how to deduce psi? So we use our vorticity equation. So if we know omega, then and we plug into here, we obtain the equation for psi is this Poisson equation. So given this, the rule of the game is to derive psi. Now, this equation is a linear equation, so it's fundamental to use it. We have to find its fundamental solution. And what is this fundamental solution? Are the solution of this equation, and the solution is called the Green function. So what is on the right-hand side is a point vortex. So the fundamental solution is a Poisson equation where the source term is a point vortex. And once we solve this equation, then the general solution is given by the integral of the vorticity with the Green function. Of course, there is all the literature given about the regularity of omega in order to assure this integral to be well defined. And we can do the calculation. And for example, we can find that it's easily to check that for the planar case, it's just a log of the distance of the particle and vortex. Okay. So now, if omega is just one vortex, we have that the stream function is just the Green function weighted by the vorticity of the vortex. If omega is the sum of several vortices, meaning several delta distribution sources, now by linearity of the equation, the corresponding stream function is just the weighted sum of the Green function of each vortex with its vorticity. Now, how to derive point vortex dynamics? We use our ansatz. That each vortex behaves a particle in the field of the other. So if this is Hamiltonian for the particle in the field of a vortex, the Hamiltonian of two-point vortex is just the symmetric version of it. Okay? So we have the two. And it's easy to see that then the canonical coordinates are just now a slightly different version of the previous one, where we have to introduce the vorticity in it. Okay. Now, I have to stress now that in general, for n vortices, the Hamiltonian will be the double sum of all these weighted Green function and the alpha vortex and the beta vortex and this product. This Hamiltonian, notice that depends on Green function when in the Green function enters the vortex-to-vortex interaction. So this Hamiltonian is describing the dynamics of the vortices, as I said, on the sphere, on the plane, or hyperbolic plane, where vortex dynamics will, a vortex will move only in the presence of another vortex. But this is not the most general Hamiltonian. This is not the most general Hamiltonian for the vortex case. And as we'll see later, we'll have to add some extra term. They will give us the self-interaction of one vortex with the geometry of the surface. So, but anyway, this Hamiltonian show this grid function depends on the distance between the two vortices in the appropriate geometry, coordinates. And so they have several, his invariant under translation, rotation for the plane. And we can see that it's easy to show these are the integrals. We have 4 integrals in Hamiltonian, the momentum, linear momentum, and the angular momentum. But only 3 are in evolution. So it means that 3 vortices is an integral problem. And this is also true for the sphere case, as we see. And in particular, we can show, it's easy to show that 2 vortices always gives rise to a relative equilibrium configuration. And this is the dynamic of 2 identical vortices, 2 opposite vortices, the dipole is a translation, and all the other cases we have rotation. Okay. Okay, so this is the review part. Now we go into business of manifolds. So we can do the same thing on the manifold. For whatever manifold, we can always build up, find the right coordinates. They give us the Hamiltonian formulas. The Z for the sphere, what is called Z. So we have here, we're taking like our theta, the colatitude, and this is phi, the longitude. And so this Z is just cos of theta. And this is, for example, already in the paper of David and Lorenzo Polvani, I think it's 93, where they study the linear stability of these rings and many more, also other stuff. And, but then we have to be careful that, for example, if we consider the sphere or whatever other closed surface, we have some extra condition that we have to require. Because now our source term, we can put on the sphere whatever vorticity distribution, has to verify this gas condition. And so we have to compensate. If I put the vortex, I would have to compensate with something else. So this compensating field actually is a sort of gauge that we have for closed surfaces, because we have an infinite kind of choice. So for example, you have your vortex, and I can put another vortex, whatever, of opposite vorticity. This will work. But what is more commonly done is to have my vortex, and then to put a uniformly distributed vorticity field. And so this choice is very practical because it links the dynamics to the global geometry. So anyways, as I said, if we do, for example, complex, we need to use this link between the G, the metric, and the symplectic form. And with this, it's easy to see that whenever we have a metric, we can derive the corresponding symplectic form using the complex structure. There's nothing else than the rotation by pi. But anyway, using this analogy, we can study, for example, what is the stability of the ring as a function of the curvature. So I have my ring, it's rotating, and now I ask myself, okay, nearby the equator, if I now play with the positive, negative curvature, how the stability of the ring change. And of course, I have to open up the sphere, a puncture sphere, in order to have some analytical continuation. And what you see in this case, you see that actually curvature is very important, because you see that positive curvature destabilize the ring, and negative curvature stabilize. So curvature is is very important dynamical parameter. And how you do that? You do this because you have that, for example, when project on the plane, you have a unique metric that is parameterized by the curvature, and so you can, at the same time, derive a symplectic form that is parameterized by the curvature, and so you have that the curvature enter in the parameter and enter also in the calculation of the famous eigenvalues of the Hessian. Now, but as I say, what happens if now we pick up our very nice constant curvature surface and we deform it? And we deform it conformally. And so we see, as I say, that our vortex starts moving. And what is entering is entering the Robin function. What is the Robin function? It's just the regular part of the Green function when you take away the logarithmic singularity at a point. And there is a big work about this Green function for the plane, a very nice paper by Fletcher and Gustafson. And for the spherical case, there is a lot of very heavy-duty geometrical result by Steiner and Okunulu. And what is the bottom line? For closed surfaces, you see actually that the Robin function is strongly related to this is the integral of the Gaussian curvature with the Green function. So this will be just the double integral of G or 0 with our K. Okay? And so we see that really there is a link of how the Gaussian curvature change and the Robin function. And this is just a constant term. So we see that, in fact, on the sphere, the Robin function is a constant, because this is a constant. But then on the ellipsoid, the revolution is no longer a constant, because this integral gives us a different thing. And so this is the Robin function, so responsible for the dynamics, for the movement of one single vortex in the geometry. So the bottom line is that now the vortex of Miltonian is gaining an extra term. Here there is our vortex-to-vortex interaction, and here there is our self-interaction, the interaction of the vortex with the geometry. And we can show this is a paper with Jay Kohler, but then we recover the same result with the paper that we have now with David, that if now we deform the sphere into some other surface conformally, we have the Hamiltonian sphere, and we have this extra term. This is the Robin function that depends on the conformal factor in a very easy way. So, and now I want to show you some simulation, because now there are more surfaces than, second, control, not escape. So I just handed this with a mouse. Just go mouse here. So just handing with the simulation. So this is our one vortex on an ellipsoid. So you see that it is going on the parallel. The parallel lines are the contours, the level surface of the Robin function, in fact. And then we have, this is usual things like this is just the regular square rotating on the sphere. And then you can see that somehow you can see the perturbing at that latitude is stay kind of stable. And we have analytical result for that. But then more recently with David, we were interested in this having the surface that have negative and positive curvature. So actually, all these simulations are David. He's the master here. So here you see again a regular a square rotating, and this is on the zero curvature point. But now, if we perturb it, then you see that the vortices spend more time into the negative curvature region here, and then the one that starts outside is kind of lost into the positive.